Science Meetup. Our focus is Julia. Julia language is one of the prime contributors. We'll talk about that, and then I'll also talk about how to use Julia and Spark from another modeling perspective. And there is a meetup group on LinkedIn, Big Data Science Universe. It's free, open to everybody. You can join and leave some comments, make some suggestions. If you want to be speaker, sponsor, or if you know someone who knows big data very well, bring him or her for the next event, and you can sponsor an event. You can take us to your company location or whatever. And I am one of the co-organizers. So what we discuss, we are organizing events for the last 3 years. We organized events at Hadoop Summit, Strata Conference, many company locations. And we talk about general machine learning algorithms, mathematics, theories, SVM, K-means clustering, decision tree. We love all those things. And implementation in Scala, Java, Python. And then we started talking about IoT, cancer genomics, ICT industry, financial services, healthcare. It's going to explode with a lot of solutions, and lots of new models are needed. So we discuss all those things. Then Hadoop ecosystems. Today I'm going to talk about something about Spark ML, Spark, Storm, Kafka, HBase, HCatalog, Hive, Zookeeper, Scoop, Flume. Anybody working on that with some interesting applications, please send me email. I'm the organizer. You can send me email directly on the meetup group. Join the meetup group and send me email. Big Data Science. Meetup group. You want to see the meetup group? Okay. This is the meetup group. If you have not seen this, there is a big universe there. Okay, so you will go deep into the universe, and then there are 3,000 members, and we are here. You can see, you can go through all the old meetups, and this is the address: meetup.com big-data-science. And I'm the co-organizer. There are other organizers. You can organize. You can be event host, anything. So it's your meetup. And then we also want to discuss and focus on OpenStack, Ambari. That's about Hadoop provisioning using virtualized servers and so on. Very interesting direction for software-defined storage, software-defined analytics, many things happening. If you have some ideas, you know someone, please come and speak. And data modeling. So all kinds of issues we discuss, and you can read about, we have it somewhere on our meetup group. You can read about all the requirements, and you can come and speak or sponsor or whatever. So today we have prime contributor to Julia language, Tony Kelman, and he's going to talk about a fresh approach to numerical computing and data sciences. And after that, I'm going to talk about combining Julia, Scala, and Spark for machine learning with CALSTATDN Model. I'll talk about new model where we can have calculus, statistics, and data normalization, and how we can use Spark, Julia, and the whole ecosystem. And then question answer. If you did not sign, please sign in the front desk. Wi-Fi is there. That's the password and login. Send me email. Sarkar@bigdata@gmail.com. You want to be a speaker in the next event, and then. That's all. I'll give it to Tony. Yeah, take it off. It's yours. You have to search for it.
Great. Okay. Thanks for having me, everybody. Thanks, for the introduction. I just want to get a sense of what people in the room, I guess, use currently in terms of your tools. I guess if you're interested in data science generally. How many people in the room use Python on a day-to-day basis? Okay, most of you. Of those people, do you use NumPy specifically? Yeah? Good for some, but not all. Okay. How about anyone use R? Yeah? Good. What about sort of Java? Okay. Scala? Okay, a little bit. All right, so Julia is a relatively new language. It was initially created at MIT as kind of a research project in about 2009, and it was publicly announced in 2012. I'll actually show you. There's the initial blog post kind of generated a lot of publicity, a lot of press. It was very. You should read it if you get a chance. The Why We Created Julia from early 2012, about everything that we want in a language. That, you know, existing tools are pretty good and we like them, but we always wish our tools could be better. So in 2012 it was publicly released, and ever since, in the last three and a half years, it's been growing with a lot of contributors now. So the idea of what Julia is trying to address is the kind of classic two-language problem of you can either have performance or you can have productivity in most existing tools. There's some exceptions of languages that do really well at both, but they're kind of rare or kind of unusual. The tooling may not be as good. So you can see, you know, conventionally that this is a kind of very public, widely seen and widely criticized plot of, you know, benchmarks can say anything you want them to, but running on a simple set of benchmarks, these have normalized performance to C, so a value of 1 is C, and then the different colors are a different set of little toy benchmarks, and you can read the code for each of these and all the different implementations. But as you can see, Julia, the idea is you can write very high level, very simple code and be within a factor of 2 performance of C without having to do a lot of effort. Whereas you can see, you know, Python is orders of magnitude slower, R and MATLAB, you know, you never really write for loops, vectorization. You always have to do vectorization with NumPy, or you know, work around recursion and use extension modules that have been compiled in C. And if those solve all your problems, great, absolutely use them. But when you need to sort of get outside of what's already there, if you need something custom, you need to start implementing your own algorithms. Either you're writing a C extension, which is not very productive, or you're working in Python and just dealing with it being slow. So a better way to look at this picture is actually not just performance on an absolute scale, but performance versus lines of code. And, you know, you can see C here, quite a bit more code. You know, Python, I think R, MATLAB are in here. So Julia is in a good place in this chart of both a small amount of code and very high performance. So just to show you, since I guess most people in the room probably haven't used Julia before, just to show you a little bit about what the syntax looks like with a simple example. Great. Okay, so I'm going to do a little toy example. I don't know if anyone in the room has heard of dual numbers before. It's a little bit like complex numbers, but instead of an imaginary component that squares to -1, you have an epsilon component that squares to 0. So this is how you would declare that type. So Julia is very, very suited to declaring your own custom types. All about, unlike a lot of dynamic languages, user-defined types can be very fast. So this is a parameterized type with the curly braces of T, saying that the value component and the epsilon component of this immutable type are both required to be the same type, and that T could be anything. So if it was a reference type, like a mutable container, you would just use the word type instead of immutable. And so here we see, if you want to now that you have this type, let's define some operations on it. You want to actually use it for something, do some math. So to extend, Julia is all about extending generic functions. So even infix basic mathematical operators plus multiplication, subtraction are actually just generic functions, and you can extend them with new method definitions for new types that you define. So first we import the generic functions for addition and multiplication, and Julia supports a few different easy function definition syntaxes. Oops. Sorry about that. Redefining types in global scope doesn't work very well. So that's where we start. So that we import base. This is one-liner function definition of plus on x of a dual number, x where x is a dual number, y where y is a dual number, is a dual number where you add the values and you add the epsilon components. Pretty simple. The multiplication is a little more complicated. Multiplication of x and y where x are dual numbers, the real components multiply and the imaginary components do a cross multiplication. X value y epsilon plus y value x epsilon. Pretty simple. So now Julia is a just-in-time compiled language that uses LLVM, which is the same underlying compiler technology that's developed by Apple and Google and many others that Clang now uses. If you've compiled C code on a Mac lately, it's using Clang. So Julia is just-in-time compiled. So let's compare, for example, a dual number where the elements are integers, so int64 here, and another one where it's y is an int64, and we can see this is LLVM intermediate representation. It's kind of low-level what this code actually gets lowered to. So you can actually kind of introspect in Julia, now that we've just defined this multiplication on two dual numbers, what does that actually get compiled to? So this is the LLVM representation, and on a 64-bit Intel machine, this is the native assembly code that that the LLVM then converts this to. And you can see it's a very small number of instructions. It's very, very close to the metal, and this will run at very high performance. Integer multiplication, integer addition, and returning. Whereas if I was to do a dual number of floating point numbers, where the floating point literal is just 0.0, here it's pretty similar. Basically the only difference you'll see is the fmul and fadd here instead of just mul and add in LLVM. And the native code is going to be mul sd and the double multiplication, double addition instead of integer. So what if we want to actually show this in a nicer form? There's a show function that we can extend. We extend what show means on a dual number instead of a default representation. We can say print the value plus epsilon times epsilon. And Julia supports Unicode syntax, kind of a party trick, but it also, if you've ever written math in LaTeX, it supports tab completion, so you can go nuts with your Unicode. Anyway, mathematicians love that. Python 3, I think, lets you do some of that. So, okay, now the other, if we want to start doing linear algebra on this type that we just defined, for example, all of the linear algebra operations, matrix multiplication, and a lot of other solving linear systems of equations, factorizations, these are all defined in a very generic way in the Julia standard library, so they can apply to custom user types with a very small amount of code for that new user type. So I need to define here what is the 0 value for a dual number. It doesn't automatically assume that 0 in each field. That would probably be a safe assumption to make, but I need you tell it explicitly that the 0 of a dual number is the dual number 0, 0. So now let's make a couple of. Here's a matrix of dual numbers, with 1 by 10 random 1 by 10 elements, 6 by 4 matrix of dual numbers. Make another one that's 4 by 3, and that was all I needed to do matrix multiplication and get a 6 by 3 array of these out. For element-wise multiplication, it borrows the notation from MATLAB here, dot times MATLAB or Octave, as opposed to in Python, I think 3.5 is the first version where matrix multiplication is now a separate operator from element-wise multiplication now. It's kind of useful to differentiate the linear algebra from the container semantics of doing the math. Another very useful functionality in Julia is effortless calling into native C libraries. So to write, there are a lot of C libraries in the world, and even though you can write code in Julia and it will just-in-time compile to LLVM that will be comparable to C speed, if you've got a library that exists and is high performance and you want to call into it, Julia makes that very easy to do. We have the C call function where you give it the function name and then potentially what library is this in. If it was a Unix, it would be libc or libm actually. But I'm on Windows, so this is already loaded. What is the return type? Is float64. What is the tuple of the input types? Here for sign, it's just float64, and then the input values. So I can call into C libraries really, really simple with no kind of glue code And I don't have to have a compiler on the user's machine to build an extension module to connect the high-level language to the low-level library. Or a little more complicated example, let's make a buffer of 25 bytes and call sprintf into that buffer of hello from C sprintf. And then what is the stir length of that, and a byte string, so get that back out. So this is kind of a basic high-level syntax introduction to some pieces of Julia. Yeah, sure.
How does Julia compares with Scala?
Kind of different. I mean, Scala is trying to combine object-oriented and functional paradigms all on the JVM. And I guess if you look at some syntax examples of if you were to do complex numbers or dual numbers in Scala, it might actually not look that different. Scala is kind of a very strict compiler. It does a lot of type checking and makes sure that your code is going to compile. So Julia is much more in the dynamic language camp of there is a compiler, but you don't have to really necessarily think about it unless you actually want to get into performance optimization. You do need to take into account how the compiler works and how the type inference. Julia also has type inference, but it's not classical Hindley-Milner type inference in Scala or Haskell. It's a little different in data flow dynamic language. So in Julia, you will get a no method error potentially if something is not implemented. It will succeed in compiling, but will give you an error at runtime. But you don't have to fight with the compiler to get your code to type check. And the fact that Julia is built on LLVM means Julia has a much nicer interoperability story with native code, whereas in Scala or Java you would have to go through the JNI, and it would be kind of messy, and not a lot of people go to that hassle. Whereas Scala and Java, of course, you have a lot of JVM Java code that you want to use. So it's in Julia does have a Java call package that will let you call into Java code, but it's not quite as widely used or well tested. I'm not super familiar with it myself. I know it's there, but it's not something that everyone in the community is constantly using. It exists, and so there's some things you can do with it. Yeah. I don't think we didn't have Scala on this version initially. I think Scala performance-wise is going to be pretty comparable to Java probably if you are good at Scala. I think the kind of the best case, like since it's JVM based, you're not going to be able to access like SIMD hardware vectorization on the JVM. But for example, like the garbage collector is really good. So I'd say comparable, but probably Julia ends up being a lot easier to use for people who've never seen functional programming.
So Julia is a functional program?
You can use Julia as a functional programming language, but it's eager evaluation. It's much more sort of in the vein of how Python would work and would feel in terms of day-to-day use than a strict functional language like Scala or Haskell.
But Python can also be written as a function.
Yeah, so it supports the paradigms. I mean, you can do map. There are anonymous functions, lambdas. There's a lot of you can do a lot of functional looking code in Julia. It's not necessarily going to be the highest performance way of writing code, but it'll work. So where was I? Okay, so this is a cool project that we have called juliabox.org, and I encourage anyone who wants to play around with Julia, but the installer is pretty easy to use, but just in case you want to just try it out, you just sign in with a Google account, and it spins up a Docker container on Amazon for you, and right now it's free, and hopefully the Wi-Fi is going to work. So it spins up a Docker container that has Julia already installed and running on it, and also the iJulia notebook, which I will show you, which was what I was working through. If those of you who use Python, if you use IPython, it's the same basic idea. Now it's called Jupyter because it supports multiple languages. Julia is one of those languages that the same notebook interface supports. There we go. So it's spinning up a kernel. Usually pretty fast. one thing I will say is if you play with JuliaBox, don't put any proprietary information there. A couple people got in trouble with their employers for overusing it for things that they maybe should have kept on their own networks. It is, we're trying not to allow information to be spread, but we don't want anyone to get in trouble. Okay, so this runs a variety of notebooks. You can also have a little console running as well. So I want to show one other notebook, sort of a generic kind of data analysis, data science, sort of in the vein of what you would do with R or Pandas, of kind of loading a data set and working through it and doing some plotting, and just to show you that these things are pretty mature in Julia. So the data frames package defines a sort of named column data structure like Pandas or like the R data frame. Here's a CSV of, this is I think some New York City housing data of neighborhoods and a bunch of various data. The read table function in data frames loads it into a data frame, and in iJulia it has a sort of nice HTML table where you can browse through things. How big it is, and there's describe, give you high-level statistics of what is the missing data. So the data frame specifically supports missing data like you would find in R Pandas. How many of these are NA, some summary statistics on them. And there's a package called Gadfly, which is for plotting, kind of in the style of the grammar of graphics, like R's, GG2, or I think it's called, Seaborn is a Python library that is similar, grammar of graphics visualization style. So, nice high-quality publication level plots. One thing is, when you first use Julia packages, they do take a little while to load the first time. But we recently, with the 0.4 version we released a month ago, we now pre-compile packages. So the first time you load something, it'll say compiling this package, and that'll only happen the first time you load it. So you can see the plots are pretty nice. I think this is an artifact of how iJulia saves the plot data. It looks a little weird, and I need to replot it. But you can color it by what borough it's in. Square foot versus estimated rent. A histogram colored by borough, income versus number of occurrences, and do various group by sorting operations. For example, group by the neighborhood. How many are there? Okay. So I think I went a little quick, but that was sort of the initial demos that I had. I wanted to talk about, like I mentioned, we have packages for interoperating with Java. Unfortunately, we don't have Java installed on the JuliaBox images. I wanted to show some of that. We have some packages for working with, I guess I can actually show. So this is a package. We have various, here, I'll talk about, so Julia's package manager is based on Git. So all of the packages are up on GitHub, and when you do pkg.add, and it clones the package from GitHub, loads sort of the most recent tagged released version. And this is kind of to show you roughly the number of packages that have been released over time. This is a package that Ian over there does a lot of the statistics and data collection pretty regularly on the state of the package ecosystem. So different point releases. We've been doing bug fix releases once a month or so. And over time, as different Julia versions have come out, there's now about 700 packages or so. And we show over time, how many of them are passing their tests, which is another interesting thing. As Julia is kind of under relatively rapid development, things do break if you're on the master branch, but we keep the release branch much more stable. And this is sort of a more generic listing, including all the summaries. So there are packages for all sorts of things. If you do any constrained optimization, numerical optimization, the packages there's various different Julia organizations as well. The Julia Opt organization is really sort of top-notch in the world of constrained optimization, and even though Julia is a very new language, the tools in it are kind of best in class already. That's pretty impressive. Otherwise, there are a lot of packages for interoperating with other systems. I mentioned CCall is built into the language. There's a package called PyCall, which, if you're used to Python and you use a lot of Python code, you can actually call it from Julia very easily. This is a package by Steve Johnson, who's a professor at MIT. But it essentially invokes the Python library as a C library, as the interpreter does. It's pretty cool, and you get one of his packages is it's an alternative plotting package that is actually a wrapper around matplotlib. So you get a lot of very familiar matplotlib functions. It's going through Python from Julia. I mentioned the Java call package as well, which is aiming to do a similar thing for calling into Java from Julia. Yeah?
How is the Julia package for machine learning algorithm compared to?
So there's a variety of them. Right now in Julia there is not one top level, let's collect all the algorithms in one massive library yet. There's a lot of sort of ongoing discussion about different forms of learning, classical learning, regressions, if you would want to use sort of the R formula style notation for some regressions, that is supported in data frames, and there's a GLM package, there's decision tree packages, so they're kind of separated by style of algorithm at the moment and a little bit smaller, but the developers of these packages are kind of trying to collaborate in, I mentioned this organization, there's a Julia Stats organization where a lot of the statistics packages are sort of developed and in communication with the same group of people. There's a pretty popular library for deep learning called mocha.jl, which is kind of in the style of Caffe. So there's a lot of activity in that area, but it isn't a single scikit-learn massive, everything collected under the same. You can call into scikit-learn from using PyCall. I think there's a wrapper package that does exactly that. So if what you want is implemented in fast there, that's...
What's the licensing?
Yeah, so the Julia main language is MIT licensed. Which is very permissive. There are some dependencies that we use that we kind of wrap and provide a lot of built-in functionality. Like much of what you would find in NumPy or SciPy right now is bundled and shipped in the language by default. A lot of linear algebra, BLAS, and LAPACK. We ship FFTW for Fourier transforms, which is actually a GPL license. So including all of the dependencies, some of them are GPL right now, but we're going to gradually move those out to be optional components and keep the core language MIT license.
So where did the name Julia?
People have pondered that question, and I don't think the developers, the main three creators of the language, have answered it definitively, other than just someone suggested it as a good thing, that a good sounding name for a language. I don't think there's a real story there. Someone's ex-girlfriend or something.
You
can pretend it's like a Julia fractal or something.
Yeah, there's the Julia set.
Yeah.
When I first actually saw the screen when the script that you showed us, it was years ago, but it actually looked like a MATLAB.
Right, and the syntax is sort of a little bit more like MATLAB than Python. We don't have the indentation sensitivity that Python does, but I'd say over time, a lot of the syntax has been moving sort of further and further away from MATLAB and more kind of into its own, like, we're a new language, we're not constrained by source-to-source compatibility, let's actually make the decisions of what we want the semantics and the syntax to be. So I think sort of the dot times, this is sort of one of the MATLAB-isms, but it's also a useful thing to separate element-wise versus matrix multiplication. So there are some convenient things. MATLAB's notation for linear algebra is pretty convenient. The backslash for solving a linear system of equations. Some of that's more convenient than doing np.solve all the time and np.dot all the time. Yeah.
How about calling C++?
That is being worked on. So because Julia is LLVM based, we have a very prolific contributor who's doing essentially embedding the Clang compiler, which is the not much beyond LLVM. It's for parsing, and that is going to be pretty cool. So it will be able to do it's a cxx.jl. So that's also. So this is sort of a little bit experimental right now, but you can do sort of you need to build a custom version of Julia right now. There's which version of LLVM you're on is a very fast changing target. But essentially it has inline C++ and can call into C++ libraries without necessarily having to go into doing the extern C wrappers and restrict yourself to a C API. Doing a C API right now works really well. But if it doesn't have a C API and you want to do C++ types, that will work. Once cxx.jl is stable and running, I think Julia's connection to C++ is probably going to be a better story than most other languages.
How do you compare it to Go language? Go.
So, very different, kind of similar in the productivity versus performance trade-off of, Go is also trying to be kind of a little slower than C, but much easier to write and much faster than Python. But in terms of syntax and language philosophy, Go is very restrictive. It's sort of designed to be super, super easy to read. There's no operator overloading. There's no generics. If you were to try to do linear algebra in Go, it would look pretty messy. It would be matrix dot dot, matrix dot add, matrix dot whatever. But Go is very, very useful for web services, which is kind of what it was written for, and scripting and doing simple, basic types, things that you would have done in Python in simple scripts, you can now write in Go and have them be compiled. So it's a very different target.
Parallel programming.
Yeah. So and Go also has a very good concurrency story. Yeah. Thank you for reminding me. That was another big part of what I wanted to mention and haven't yet. So Go supports coroutines and channels, which is very useful for local on a single node, having many, many threads all working on different pieces of a task and cooperating. Julia has supported since the very beginning distributed parallelism, multiprocessing. So there's you can add procs and get yourself multiple nodes. This is the REPL. So if you're not using through iJulia, this is the basic sort of command line console version of Julia, but you can do add procs and get 4 worker nodes. And then there's there you go. So Julia supports distributed parallel processing. So when you did add procs, it actually fired up separate Julia processes on the same machine. It also, you can use SSH to do this on remote machines as well. So you can do distributed over a cluster to have multiple processes of Julia talking together over TCP/IP and do potentially very large-scale parallelism. There's a distributed arrays package for doing very large-scale out of core memory. Very recently, there was a pull request from some collaborators at Intel Labs merged that also support threading. So on a local node in shared memory, we will also support, once it's enabled by default, also using threads on a single machine in addition to, this is in parallel, the at parallel, there's a PMAP as well. There's a set of message passing primitives where you do remote references and remote calls to communicate. So that's Julia's built-in parallelism functionality. And it's much more kind of focused on, I guess, data parallelism rather than concurrent task concurrency. We do have coroutines and tasks as well, but they're more green threads and not. So.
Does the fact that you use LLVM for just-in-time compiling mean that you can generate libs, C libs?
Say again?
Does it mean that you can not only generate, not only compile just in time, but also generate libs for using in?
Oh, okay, you say like ahead of time compilation of a library kind of thing. So this is something that kind of works right now. You sort of have to use the embedding. Like I mentioned, packages are now precompilable. So when you load a Julia package, it is actually caching the generated code to disk. It's not necessarily usable in a really, really easy way yet, but that's a target that is being developed on, and doing compiling to backends. We also work on ARM, for example, because LLVM has an ARM target. But making sort of more standalone libraries that can run without Julia present is something that it's a hard problem, and there's a lot of people looking at doing that and making extension libraries for Python in Julia or in R for Julia. Right now, you can do that through the embedding API. So there is a way of calling Julia from Python and calling Julia from R, sort of the other direction. But it's not really. You sort of need the Julia libraries to be present at the moment. Yeah.
You mentioned you could run it on some multiple nodes in parallel at the same time. What's controlling, or how do you configure the number of nodes, or how that distribution occurs?
Yeah, so we have kind of a machine file format that you can give to set a specific. Let me see. There we go. So there's a kind of cluster manager API that we can use to set up on various existing. If you have, for example, a Yarn cluster or a Slurm or a SunGrid engine or an NPI-based cluster, different schedulers that we can integrate with. There are different predefined configurations that Julia's add procs can hook into.
Can the scheduler become part of the federations? Does it federate across different networks, or do you have to stay within the boundaries of a single subnet or something like that?
I don't think so. I think you can give a general purpose IP address to the cluster in the cluster manager format, and I think it needs a passwordless SSH at the moment. So if you have the keys set up properly, it might be a little tricky to set up, but it should work.
So you mentioned Yarn. I didn't actually hear all of it, but when you program this, you use this big data platform.
So there are
What type of platforms do you actually run this?
People have used it on a lot of different configurations. So I couldn't tell you off the top of my head who is using Julia in production on a very large, Hadoop type cluster right now. I think there might be people who are doing it, but it's a little early for that. It's not 1.0 yet. It's very, very usable kind of as an analytics language for rapid prototyping, interactive development, and we are certainly trying to make it more and more robust to scale to very large problems, but a lot of the parallel underlying pieces of functionality are being kind of ongoing. It's kind of ongoing development. So I think I showed briefly this LE package. This is a package that has been made for doing a Julia cluster manager that would run on HDFS and Yarn. I should try it out. I wanted to actually show a demo that was using this, but like I said, the JVM HDFS stuff wasn't quite set up on the machines that I had access to yet. But yeah, so a lot of the high-level Julia add procs, at parallel, spawn, PMAP, simple parallel APIs would kind of seamlessly work. And I think this is actually calling Hadoop and Yarn through protobuf, which there's a package in Julia for doing protocol buffers, and I think one for Thrift as well. I don't know if that answers your question.
Yeah.
So I don't know if you've done any performance benchmarking across nodes in a cluster versus what you might do on a Apache Spark distributed node. Do you know what that looks like?
So it's being worked on. I think there are some numbers. I would be a little hard pressed to find them. There have been some benchmarks on communication latencies and bandwidths.
Okay, so let me ask you this: the scheduler. How is a scheduler benchmarking compared to what's happening? Because you're using a different scheduler, right? It's a native scheduler you're using instead of using Spark scheduler.
Yeah, I think I think some of the cluster managers have fairly naive schedulers on them. So I guess I'm not sure. Like we haven't written a really sophisticated directed acyclic graph computation scheduler like Spark has a very mature scheduler, and I think for a lot of kind of Spark integration is something that a lot of people ask us a lot about, and maybe I wish we'll talk a little bit more about it, but sorry, terrible names. So there are several different ways that could be designed. Do you make an RDB in Julia implementation, or do you go through Java all the time? And is there a lot of sort of serialization back and forth to go between the native Julia object representation and the JVM Spark object representation?
So it's application specific.
Yeah.
It depends on how much you're passing, what you're passing back and forth.
Right. And I think so. I guess right now Julia is kind of much more popular in academic users. And a lot of people are using Julia over MPI on sort of classical supercomputer HPC clusters, and that works pretty well. And MPI is very high performance, low latency, but not necessarily going to work on a commodity machine. But the interconnects aren't set up the same. So the right way to do that is still a kind of open question. Maybe someone will write an embedding client to call Julia from Java. I don't think that's been done yet, but it certainly could be doable through JNI. There's a lot of potential possibilities of how you would do that. Rebuilding Spark from scratch would take a lot more man hours than we have. I'm not sure anyone wants to do that, but there's also potentially a price you pay in, you get fault tolerance and resilience, but the price you pay for that is performance and not necessarily. It's hard to control data locality. I think that's kind of a big scaling challenge of being able to control where data and computation happen and make sure that there's not unnecessary movement of either of those things. And really kind of need more fine-grained control, I think, if you really want to stretch to advanced linear algebra computations, things that are a little more sophisticated with fine-grained point-to-point communication. So there's a lot of interesting challenges in the parallel computing space that Julia is trying to play a role in. We'll see. All right, so I think that about covers my time. Thanks for your attention and questions.
That was a great introduction. No, it's not HTML.
No?
I think
It should find it.
Oh, I see.
It should. No, can't find it.
USB or what it is? Computer?
Yeah, this is kind of. No. Maybe this will.
No, I don't have HDMI.
Oh, okay. It was working before.
Yeah, it was working before.
Okay. Are you on? Let's try. Here it goes. Okay.
Okay, hello. Well, I'm the co-organizer and also inventor of a model, and I'm trying to make it popular. And so this talk is about a model called CALSTATDN. First, I cannot, it's already 7:45. I cannot get into details of the model, but there is already a YouTube video. If you just search for CALSTATDN, you can see that and think about it, send me questions. So I'll go over the main points, and the focus of this talk is about how we can exploit power of Julia, Spark, Scala, machine learning, and so on. So as Tony mentioned, there are tons of things in Julia. I'll show you the set of library packages. Here it is. See the list of things they have written. It's about algorithms. Name about any algorithm, it's there. And then checksum, pattern matching, then data structures, all kinds of arrays. You can visualize arrays in many different ways. And then machine learning, look into the names you see in big data space. Everything is there. Neural net, backpropagation neural net, decision tree, deep learning, K-means clustering, everything is there. So this is an attractive language. A lot of scientists working on that, and you can do Google search and see that people are replacing MATLAB with Julia. High performance, he mentioned about LLVM, JIT compiler, but Spark and started with completely different vision. It's cluster computing, big data, suck up lots of data in memory, do some machine learning there. So the focus is little different from Julia. So if we can combine the two, power of Spark and power of Julia, that will be ideal. So yes, there are some efforts. He mentioned about parallel computing possibilities in Julia, then some kind of Spark implementation RDDs, but then I saw some discussions in Google group that that's not the way you implement RDD. So I did not dig through the code. So I became a little nervous. So I have a proposal for that, and I'll get into that. And this is my goal. That there is a, by the way, there is a co-inventor also for this model, and he is a junior programmer, just a high school kid. Anyway, I learned calculus from him. I forgot about calculus. I became a programmer, so I had to dig through the calculus. So what is the motivation? Motivation is everything is coming over the internet. I mean, you name about smart cars, smart cities, cancer genomics, bioinformatics. Everybody can have a small capsule, and something can monitor your body. And so tons of data will be sent over the internet, and you have to store them. You have to do machine learning. You have to find out some hidden knowledge, and then take some action. And it's a non-trivial thing to do with petabytes of data with all kinds of 4 V's, volume, velocity, variability, and so on. So the question came to my mind, along with many other people, that well, machine learning, it's great, nice, interesting algorithms, K-means clustering, support vector machine, but most of them, they have exponential complexity. I mean, the data set becomes larger and larger. It will take more and more time, and might go from 1 to 2 days to a month or more. I mean, it's power of something, a to the power dk plus 1. I'll show you the complexity of K-means clustering. And so most of the statistical computing algorithms, they have very bad complexity. I mean, scalability issues are there. Whereas, I mean, statistics is a great, what should I say, some component of mathematical studies. What about calculus? That was there for 2000 years, but it's not there in machine learning. So calculus is everywhere, but you can find rate of changes. It makes life easier in economics, in physics, everywhere. So why can't we bring it to machine learning? So we started thinking about that this is the flow diagram, and you can see some big professors at Caltech and many other places. They talk about this flow diagram without this block on the right hand corner. So basically you have a function, unknown function fx, for a large data set, and you want to find out what is that function. So you will find the probability distribution of all the values, and you will sample things out of that, so that you can train a model on the samples, and by inputting some hypotheses, and find the best hypothesis that captures the patterns inside the samples, and then use that for prediction. That is how machine learning works. So in CALSTATDN model, we thought that, well, the level 0 values for domain elements, that's great. But what about if we can include rate of changes or derivatives? So a variable is changing with respect to another variable, first derivative. We can have some values. We can have second derivative, third derivative, or nth order derivative, and we can have probability distribution of all those things. So we can feed that to training samples as well. And then the hypothesis can be having both statistics-based model like clusters or regression or decision tree, but there can be calculus-based model as well. You can have double derivatives related to some rate of change with respect to time and so on. There are equations all over science books. So this is where it started, and we did some smart home analytics system studies, and we found some enormous gain in performance. And we found that the error also will be something very interesting if you use calculus. The error, the best hypothesis you find, Gx, that will be very close to Fx. And the error estimate, that's another big area of studies. There are some professors working on PAC models, probably approximately correct. And this error will be much less than any other statistical computing machine learning paradigm. So I have to get into the implementation part, so I'll go a little fast. So there is a workflow model. So machine learning as a workflow, and it is evolving very recently with Spark ML as well. They have a workflow. I'll get into that. So machine learning as a workflow, you get your GX, your hypothesis that you discovered, and then apply with some calculus-based model. And then immediately followed, immediately after that, you apply some statistics-based model like clustering. So you take some derivatives, then you apply some clustering or regression on the derivative values. And statistics-based models are nothing but generalization of a set. So if you have a set, you do clustering, you get a generalized value. That's very close to what we use in relational databases. That's a primary key. So if you do k-means clustering, you can get cluster ID 1, 2, 3, 4, and there is nothing wrong using them as primary keys and as foreign keys. So if you are consciously modeling with the output of statistics and you consider the rate of changes, then you can really normalize that data set. Okay. Now normalization, people might say, man, normalization, you are computing something in real time. Where is the persistent data normalization? Everybody is using data frames. They are writing onto databases, reading from databases. So it's not a big deal. We can do that. So if you normalize your data, which is the output of statistical computing, you can make queries, SQL queries. So once you make SQL queries, you can have parallel partitions for the next level of machine learning. So machine learning is a loop going through from different sets of attributes you are focusing on. If you have 50 attributes, you can go for 5 attributes, find the rate of changes, apply statistics, then the next 5 attributes, and so on. And once you are satisfied, you have a big database, call it a data warehouse or whatever, and you can make queries, and they have some derivative values. You can apply anti-derivatives integration, and you can get some graphs very nicely and with much better performance. So this is the basic idea. So this is database, how it is growing in the normalized relational model. That you have the main table, you apply your hypothesis, you get the first level of normalization, and then in the next iteration you apply again the same hypothesis on these two tables, and you get the next level of normalization, level 2 normalization. So this is a different picture than how you model your enterprise data sets. You know the keys and the dependencies, employee, salary, and all those things, and you do third normal form or whatever with predetermined knowledge how the things are related. But here things are hidden. You have to apply statistics, apply calculus. It's big data coming from somewhere. You don't have any idea what they are. Okay, so that's the whole idea. So we took some data from Intel Berkeley lab. It's available over the web from UC Berkeley. And then we applied, that's from sensors on the ceiling, and it's for a smart home analytics system within a lab. So we took heat equation. It's a well-known equation for how the temperature changes in a three-dimensional space. So it has double derivatives of temperature with respect to x, y, and z coordinates, and constant of proportionality, and then dt and dt, how the temperature changes with time. That's our calculus. And k-means clustering, that's our statistics. So you have sensors on the ceiling. You can do spatial clustering. So you can find out this portion of the room, how the temperature is changing. Okay, and then what time of the day. So you have spatial clustering. Next you can do temporal clustering. So this is how statistics can help you to analyze. And so that's what we did. And if you have all the data, put onto MapReduce system and do k-means clustering, and that's the practice right now. That the complexity, n to the power dk plus 1 log n. N is the number of records, d is the number of attributes, k is the number of clusters, and then log n, just plug in some values, 200 clusters, 50 attributes, 3 million records. It's a very, very large number, and it might take days. So the scalability wise, it's not a very good complexity number. If you normalize things, you query, and then you can narrow down your machine learning. You don't have to find everything out of 1 billion records. You know from the first 10 attributes that this is good, I like it. Now I'm looking into what happens with a constraint set on these attributes I already perform my machine learning on. So it's a query, and then you focus on narrowed down kind of data set and do your machine learning. So just like the way you query things and then you think about what will be my next query, same story over here. You can do that with exploit the power of relational model. So here is the thing. This is the workflow, and I'll talk about why it is very interesting to match with what Spark is doing. So it's a pipeline starting from the sensor networks here. And here is a big table sensor data. You have XYZ coordinates to represent each sensor in a sensor network. Take the spatial clustering using k-means clustering and find the primary keys, that is database normalization. And then for each spatial cluster, you partition the record sets. For each record set, you store into some tables and normalize table and apply some computing for double derivatives. I'll get into that, how double derivatives can be computed on relational records in a table. Basically, one set of values for an attribute with respect to another set of values for another attribute. So after doing all those things, you can do date time based clustering and create another table and so on. And finally, it goes to integration technique. Now, you can read about that. You can watch the video. A lot of details are there. But this is the most important part, that the whole workflow I just showed you, it's a gigantic equation. Actually, because of calculus and statistics and normalization, you see that equation. Probably you have not seen that kind of equation, that I have integration. There I am using some notation, data normalization, and stat for statistics. There is k-means clustering on date time, and here is the relational join. So I have relational operations from relational algebra embedded into this equation, and it has also integration, differentiation, everything. And here is the calculus expression, heat equation, and x and y, they are the symbols to be replaced by this. Compute dtemp dx to the double derivative, normalize on this table, which is auto increment table xx. Xx is defined in the next level over here with statistics over k-means clustering on xy coordinates and so on. So the whole purpose is to deliver the message that this equation is a very big equation, symbolic, functional representation, nested functions. If you flatten it out, it can be like a Spark pipeline with many functions added to each other. And sometimes I can embed things borrowed from Julia function. I'll get into that. So this equation, just like relational algebra, the way relational database optimizes queries, if you have cost functions, just plug in here and there, you can get the overall cost estimate for the whole analytics workflow. That possibility is there. Machine can do that. Some machine can optimize the whole thing, which is not existing right now. So this is the power of having the mathematics, everything bundled into one big expression and one big equation. And why it is interesting, we are dealing with streaming data from sensors. Data sets are coming every second, every minute, and there is Spark streaming, Spark integrated Kafka, Flume, HDFS, Kinesis, everything. And there is something Spark ML, that is Spark pipeline for machine learning. I'm going to look into one such example. But they work on something called data frames. Data frames are nothing but tabular representation of data while you are computing. It's not from it may be from a relational database, but while you are operating on that using Julia function or Scala functions, they are like data arrays in your transient memory. So Spark ML works on data frames. They manipulate data frames all the way for predictions or getting a model. Same story over there. Julia has also data frames. And the interesting thing is now the data frames can be persistent. You can read from a CSV file or text file, or read from a relational database with a SQL query, make it a data frame and operate on that. And Julia also does the same thing. I'll give you some examples. Then we can pass all our data sets via data frame and go from Spark environment to Julia environment. It's seamless because both are manipulating data frames. So we can write to HDFS databases or dashboards or whatever. And here is the thing, example of data frames with Spark. You can see that from JSON file, you create a SQL context, and then you just do print schema. It will show you the schema, what was there in the file. There was age, there was name, and here it's all functions concatenated one after another. But it looks like as if it's a SQL query. So see the output: name, Michael, Andy, Justin. And then again, select data frame this age +1. So you are computing something, adding, incrementing something, and age is added. So it's like SQL queries. And on the last statement, you can see it is selecting something from a table in a relational database. So everything is possible with data frames. You can read from tables or CSV files or data files or anything. Now this is the Julia perspective of data frames, that you can read from CSV, TSV, text. You can also write into output CSV, dat file, and then these are the two variables, names and jobs, and you can do join, inner join, left join, right join. So that's a very powerful concept, very close to SQL paradigm, but it's happening all online in your Julia environment, and then you write it back, and then Scala can read it, or in the Spark environment you can read it. So let's look into Spark ML, and they operate. It's a pipeline, and they operate on data frames. The documentations are all there. So Spark ML uses data frame from Spark SQL as an ML data set. So they don't care about creating an array or whatever. Data frame itself is the data abstraction they use, and they can hold a variety of data types. They could have different columns storing text, feature vectors, true labels, predictions, and so on. And then there are transformer. Transformer is a particular, what should I say, state in the workflow. A transformer is an algorithm which can transform one data frame into another. Example, ML model is a transformer which transforms data frame with features into a data frame with predictions. Then there is estimator. Estimator estimates which particular model fits into a particular data set. Pipeline is the overall chain of things, and then parameters. So here is the example that it's from the Spark ML documentation, that you can really tokenize something, hash on that, get a logistic regression model, and that's the fit, pipeline.fit. Fit will do that, fit a model properly with this data coming in. But I have added this black box with Julia. Julia can do lots of machine learning, logistic regression, backpropagation, neural net, and so on. So through a data frame, I will make data persistent and then read from Julia and do that. And Julia doesn't have to re-implement. Yeah, please.
So the point of integration between Spark and Julia, so you convert the Spark data frame into Julia data?
Yeah, so they both can read from text file or CSV file or from relational database. Okay, so I just create a data set, store it into a database, and transfer my control to Julia, and they can do the computing, store it back. Spark will get the result back.
So Julia can access the Spark cluster.
Okay, so that's the issue of re-implementation of whatever Spark already did. They worked on big data for quite some time. They have clustering, they have machine learning happening in the memory in parallel, and certain things are not well founded in Julia with respect to RDD and so on. So we can embed the call to Julia functions through CAPIs, and that will be through JNI. Java and Scala, they talk to each other seamlessly. You can have CAPI calls. You don't have to pass any parameter and slow down the thing. It's going to data frame. So the whole ML workflow pipeline, that will work perfectly all right. You are reading and writing through some data, persistent data in text file or CSV, and you make use of the scientific strength of Julia. At the same time, the big data strength in Spark is continuously getting added, new features, and you are utilizing that. So this is the whole idea, that in CALSTATDN model, now I can get back to the model I just talked about, that we need calculus for machine learning, then statistics, then data normalization. So here is the calculus in Julia, and it's pretty fast, and it can work on data frames. So here is CALSTATDN, the model. I use calculus if I need, or even the statistics in the Julia environment, bring back the data, use for a model in Spark environment, and they are used for streaming data, which is powerfully existing in Spark streaming as of the latest version, and do some predictions. So those things are all possible. On a cluster, I just copy Julia libraries or environment in all clusters, just copy it and embed under Java and JNI and so on. So only small thing, I mean, it's not a big design, that Julia functions you have to call to transfer the control from Scala to Julia. That can be an abstract class, a trait definition. So trait, if we use a keyword Julia def, here is a function written in Julia, and here in Scala we do this, and then this trait can be extended by other classes, and by default it will go to Julia when you call that through CAPIs. And there is no transfer of big parameters or anything, it is going through data frame. So that's the kind of thoughts I have. I'm continuously exchanging ideas. Anybody interested? This will be interesting development. That's all I have.
So, question. So you're using the pipeline, and then you calling Julia to use arithmetic functions, and that's kind of a fixed workflow, right? So could you do a reverse, have Julia, pass data to have,
Yeah, I mean, through data frame, I mean, we don't want to mix the two paradigms. One is object-oriented. Lot of features are there, abstract class, this thing, that thing, functions, and polymorphism and so on. Julia is just level 0 function. It just define a function, it can be called from anything. It's pretty fast because implemented with C, with LLVM and all those things. Scala, sometimes they're not very fast. So we don't want to mix the two. Give the data frame, give the data, let them do something, and we use the result there. That's the best opportunity at this time. What will happen in future, I don't know. I'm talking about what is existing right now. It works fine. Because this ML, Spark ML, they are frequently writing onto data frames onto persistent store and reading back and doing their things.
So in Spark, there's some machine learning libraries, right? And also
ML, yes.
Yeah, in Julia, there's also some machine learning stuff. So in terms of choosing, when you try to process data and build a model,
I think somebody has to do benchmarking and give some dots here and there, and
yeah,
ML doesn't
which library
work.
is better? You using Julia machine learning library or Spark?
Well, the thing is that lots of work has to be done from academicians. The sensors will be everywhere. You are looking into heat transfer or smart car or smart home. you need some physicists to do that. So they will like to have some scientific computing paradigm seamlessly integrated with big data. So you have to see both ends, that not just someone from MapR can solve it as a big data problem, but somebody sitting at MIT can invent something new in scientific computing, and we have to use the strength in both ways. No more?
Are there any links, references where I can read more about it?
You mean the presentation link? I'll
The
put it.
presentation link and probably.
Oh, I did not show you. I mean, I myself was studying, and so much of material is there. See, I kept everything open. This is Spark ML workflow programming. This is creating data frame, and here you can see some interesting thing. It's happening at Databricks. They're a Spark company, and they integrated Spark streaming with machine learning. So read this blog, introducing streaming K-means in Spark 1.2, and they are using some visualization, real-time visualization things. So pretty interesting and latest things we can do with Julia also. Julia, and then the Spark environment, you can do this. So visualization part, we can do it here. And then this is about data frames I just talked about, ML programming, and this is Julia. Julia has so many things. I could not try all of them. I tried only a few of them. They have something about Spark, RDD, but then I got very bad comments on Google Groups, so I stopped using that. This is about Spark streaming. You can read that, and they're developing lots of interesting things with functional programming. One such API can go to Julia and come back again. So that is how simple integration can be. So you can have .api, one can go to Julia and come back. So that can be done. This is calculus. They have, well, we have to extend this if we want to use it extensively on scientific data. Yes, it works, but it's like some college students solving it on a machine. It has to be production scale with large big data. So this has to comply more with data frames and persistence and so on. I was studying data frames also. Lots of things are there, but not much with. They mainly read from text files or make them data arrays. I want more SQL to be present, insert within code. Scala and Spark has that, but there should be more like that in Julia. And that's all I have. So a lot of things to study.
So Spark is a process engine, and Julia is like the final output or.
No. Julia is also a processing engine.
Okay.
For certain scientific computing like calculus, okay, or some very complex regression model that needs a lot of computations. Okay, Spark may be slow, Julia is fast. So you just create your data frame, write it, Julia can read it and apply that, and you read it back.
But Spark itself can do the computing.
Well, Spark is object-oriented, and they have all kinds of interesting things, parallel computing, everything, but there is not many benchmarks that this is really fast and things will not crash. They read from MapReduce. It's still experimental. A lot of things are happening even now. So that's all I have. Thank you.